Hello my dear students, welcome to video number 139 of my channel MALACHEMPHILIC. And this video number 139 is the 78th episode of the course Chemical Thermodynamics, but the topic is Thermochemistry Part 4. Thermochemistry Part 1 to 3 already I have discussed in my previous videos. Let's see what is there in Part 4. Thermochemistry, this content already I have shown it to you earlier. Among these topics, I have discussed enthalpy of reaction, enthalpy of formation and enthalpy of combustion. Today I am going to discuss enthalpy of transition, enthalpy of phase change and enthalpy of reaction. So let's start. First one, enthalpy of transition. See here, this graphite, that is the one allotropic form of carbon, is converted to diamond, that is another allotropic form of carbon, and heat involved, that means heat absorbed or released during this process, that is enthalpy of transition, and it is delta H naught, that means in the standard condition, that means the heat evolved or absorbed when 1 mole of this allotrope is converted to another allotrope in the standard condition, that is 1 atmosphere pressure. So, heat involved when a substance is transformed from one form to another allotropic form, that is enthalpy of transition. Now coming to enthalpy of phase change. Let's see. See, this liquid is converted to solid. Liquid is converted to solid means from one physical state, that is liquid state, to solid state, and this process is freezing where heat energy is released. And the second one, solid is converted to liquid. Here it is, in this case it is called the fusion, where heat is absorbed because solid is converted to liquid. Okay. Now, during this change of this physical state, that means when one substance from one physical state is converted to another physical state, the heat energy absorbed or released for 1 mole of the substance at 1 atmosphere pressure, that is the enthalpy of phase change. In the first case, it is enthalpy of freezing and this is enthalpy of fusion. So, heat absorbed or released when 1 mole of any substance transformed from one physical state to another. Now coming to enthalpy of neutralization. Here the heat evolved when 1 gram equivalent of an acid reacts completely 1 gram equivalent of base in dilute solution. That means 1 gram equivalent weight of acid is completely neutralized by 1 gram equivalent weight of base in dilute solution to form salt and water. That heat involved is known as the enthalpy of neutralization. Now, in enthalpy of neutralization, I want to discuss some more points. See here. 1 minute. Here in enthalpy of neutralization, it is exothermic nature. Exothermic nature. What does it mean? It means that during neutralization, heat is always evolved. So, during neutralization or acid-base neutralization, heat is released. Okay, heat is released means this delta H of this process or this neutralization, we can say that will be negative because heat is released. Okay. Now we'll discuss another point. Say neutralization reaction of strong acid and strong base. Strong acid and strong base. You can take any strong acid and strong base. That means if you want to perform the neutralization reaction between any strong acid and strong base, then heat evolved. So, heat evolved during this neutralization, What neutralization? Neutralization of strong acid and strong base. During this neutralization is constant, and it is equal to 57.1 kilojoule per mole. Why? We know that strong acid and strong base, they undergo complete neutralization. So when you are taking 1 gram equivalent weight of strong acid and 1 gram equivalent of strong base, that means 1 normal solution of strong acid, 1 normal solution of strong base, acid and base will be completely dissociated or ionized. So whatever H plus ion present in acid or whatever OH minus ion present in base, that is completely ionized and they are in the solution. Completely they are in the solution. Okay. So the net reaction, that is the H plus in aqueous solution plus OH minus in aqueous solution, it is giving you the liquid water with, and this is for all the ions, all the H plus and OH minus ions of acid and base. Okay, because whatever that H plus OH minus ion present in the acid molecule and base molecule, that is completely in the solution because they undergo complete dissociation. Now, another point I want to discuss, that is the weak acid strong base. Say weak acid strong base, or the reverse one, that is weak base and strong acid. Here the heat of neutralization or enthalpy of neutralization is less than, here the heat of neutralization is less than neutralization of strong acid and strong base. Why? Because here one part is weak, either weak base or weak acid. So weak acid or weak base, they undergo partial ionization. So to make complete dissociation or ionization, you have to supply energy. Energy is required. And during the neutralization reaction or during the formation of water by neutralization reaction, energy is released. Though energy is released, but some energy you have supplied, some energy is required. So net energy released will be less than 57.1 kilojoule per mole, which is released during the neutralization of strong acid and strong base. So what I should write? That here, first case, what happened? First, energy is required to ionize completely the weak component, that is weak acid or weak base, weak component, right? Therefore, what happened? Energy released during water formation is reduced. So when it is reduced, then what happened? This delta H of this reaction will be less than this 57.1 kilojoules per mole. Okay. Here I should write minus 57 because energy is released. Right? Now, let us solve this problem, numerical problems. The enthalpy of neutralization of hydrochloric acid by sodium hydroxide is minus 57.1 kilojoule per mole, while the enthalpy of neutralization of ammonium hydroxide is minus 51.1 kilojoules per mole. Now, what you have to calculate? Calculate the ammonium hydroxide dissociation enthalpy. Okay, this is the problem and options are given. Option A 14 kilojoules per mole, option B 6 kilojoules per mole, option C 8 kilojoules per mole, option D 10 kilojoules per mole. So let's solve this problem. Okay. Now here you see, first of all, it is sodium hydroxide. That means when the strong base sodium hydroxide is neutralized by strong acid HCl, that is hydrochloric acid, the reaction is, what is the reaction? Already I told you, the reaction will be nothing but the complete H plus ion which has come from the acid, completely ionized, plus complete OH minus ion or all the OH minus ion, and it is giving the liquid water. And say this is equation number 1, where your delta H, I am writing 1, first reaction, it is minus 57.1 kilojoule per mole. Now, what is the second case? When weak base ammonium hydroxide is neutralized by what? Same strong acid, hydrochloric acid. Then what is the reaction? The reaction will be this H plus in aqueous solution plus ammonium hydroxide, because ammonium hydroxide is not completely dissociated. So this will be your ammonium ion, this is aqueous, ammonium ion in aqueous solution plus water liquid, and this is equation number 2, and where your delta H, enthalpy of this neutralization reaction, is minus 51.1 kilojoules per mole. Okay. Now you do equation 2 minus 1. What we will get? Equation 2 minus 1. So, H plus aqueous plus ammonium hydroxide aqueous minus equation 1, H plus aqueous minus OH minus aqueous is equal to, what is there? Ammonium ion aqueous plus liquid water minus liquid water. So now see, H plus cancel, water cancel. So what is left over? Left over is ammonium hydroxide aqueous is equal to, we can write this ammonium ion aqueous, OH minus OH minus, if you take this side, that is OH minus hydroxyl ion aqueous. So this is nothing but the dissociation equation of ammonium hydroxide. So what is the dissociation enthalpy? That means your dissociation enthalpy will be delta H of reaction 2 minus delta H of reaction 1. What is delta H of reaction 2? That is minus 57.1, then minus 51.1 minus of minus 57.1. So it will be your 6 kilojoules per mole. Okay. So the answer is option B, that is 6 kilojoules per mole. Hope it is clear. Thank you.